Hi, everyone. I'm excited to introduce Eran Malach, who's a PhD student at the Hebrew University of Jerusalem, um, working with Shai Shalev-Schwartz, and he's interested in the theory of deep learning. And today he's going to be talking about learning parities in neural networks and a series of papers on the topic.
Right. Thanks for the introduction. Yeah, feel free to interrupt with any questions, and I'm not sure like what the time frame is, so just let me know when you're tired with some topic. We can go to the next one. In any case, yeah. So this is I'll be mostly focusing, I think, on the first and last works here. So the first work here is with Amit Danieli, who's also in the Hebrew University. It's about learning parity with neural network. That's the title, and it's mostly about comparing the ability of learning parities using neural networks versus kernel machines and linear models. The last one is a very recent work with a bunch of people at Harvard and Microsoft. It's about hidden progress in deep learning, and this is also involves parities in kind of a slightly different setting. And maybe I'll mention another work that we had that also touched on learning parities. So in different settings, this poses an interesting problem. Yeah, feel free to interrupt or ask any question, and yeah, I'll be happy to answer. Okay, so I'll start with some motivation. Again, I don't know, like some depending on the crowd, some people really like these kind of parity or synthetic mathematical problems and find them intuitive, why they are interesting for studying in the context of deep learning. Other people, to other people, it looks like too synthetic. So I'll try to kind of motivate why we're even studying these problems. So I started with kind of like the basic question or a basic question of machine learning theory or supervised learning theory, which is what problems would be easy or hard for machine learning algorithms in general to solve. So again, it's a kind of a supervised learning setting. You're getting a sequence of examples labeled by some function. And it turns out that, well, we have a very good candidate for easy problems or easy functions. These are linear functions that are studied a lot in the context of learning. And I mean, there's a lot of reasons why these functions tend to be easy to learn. And my intuition here is at least one way to think about why this is easy for machine learning is because a small change in the input in the context, in the case of learning linear function, causes relatively small change in the output, and change in the output is correlated to what we changed in the input. So the output depends kind of nicely on the input. And in the case of parity functions, which one way to think about them is like linear functions where we put modulo 2 at the end. So if we think of the function as being a sequence of bits, the weights would be 0, 1, the input bits would be 0, 1, and then instead of just outputting the sum of the weighted sum of the inputs, would output the weighted sum modulo 2. And in this case, a small change in the input can cause a big change in the output. When we're flipping a single bit would cause a big change in the behavior of the function. So this kind of makes this problem extremely nonlinear or behaves in a very weird way, in a very kind of like high frequency dependence on the input. So this is kind of like for motivation, why these kind of parity problems are hard to learn. And I'll define everything more precisely and formally, but this is just kind of for intuition why these problems tend to be hard. And why do we want to study them in the context of machine learning? So one reason is, basically one immediate goal of machine learning theory would be to kind of understand the behavior, be able to compare different algorithms for machine learning. And when we're studying easy problems, this is done a lot. There's a lot of work on learning linear problems or something that problems that behave linearly. And this includes kernel SVM or kernel machines. In this case, a lot of algorithms can solve these problems because these problems tend to be easy to learn. But the fact that these algorithms can solve these simple problems does not tell us necessarily which algorithm is better, right? So a linear function can be learned using a perceptron, SVM, decision trees, neural networks, and in different settings. And they're all performing pretty much similarly, but this doesn't really tell us which one would be better. But in the case of hard problems like the parity problem, we can use this problem to differentiate between the behavior of different algorithms. Because we're studying a problem that is specifically designed to be hard, this kind of like exposes which algorithms tend to be better or worse than others. So this is at least my view of motivating why these problems are interesting. So to make things more formal, so what is the parity, or specifically the Nk parity problem would be defined as follows. So you're given a sequence of n bits that are drawn from some distribution over the unit, the Boolean cube, or I'll take the bits to be plus or minus 1, which will simplify some notations. And within these the sequence of n bits, there's going to be an unknown subset of size k, and we usually think of k as being small subset of the bits. And the output would be the product of the bits in the subset, or in other words, if the number of -1s in this unknown subset is even, then the output would be 1, and otherwise the output would be -1. So this is just a way of defining a supervised learning problem. There's an input of size n, and the output is just 1 bit. So binary classification problem. And I'm going to denote the parity function over the subset A by phi of A.
Just to clarify, the task for the given task, the subset is a fixed set. It's just harder because the network doesn't know which subset it is.
Yeah, so you don't know what the subset is. You're getting a sequence of n bits, and for each bit you get the parity of the bits in the subset. Of course, you don't. If you know the subset, then there's no problem. Right? Mm-hmm. So the problem is you're given a data set of labeled examples, and the answer for each example is the parity of the bits in this small subset of relevant bits, this subset A. Okay, this is how we label the examples. All right, that's clear. Okay, cool. So yeah, feel free to interrupt with further questions. Okay, so this is just a supervised learning task, and which turns out to be hard. So there's a lot of literature on the hardness of learning these kind of problems. I will. This is all mentioning previous work, so this is not something that we directly worked on, but we're using these results to show specific hardness results for kernels. But generally, the problem of learning parities over the uniform distribution turns out to be hard for gradient descent, specifically for gradient descent or gradient-based algorithms. So specifically, the algorithm that I'm focusing on is the what I would call the noisy population gradient descent. So this is kind of like a theoretical algorithm. This is not something you can implement in practice. What you're getting, you're updating your weights based on the gradient over the population. So this would be the average gradient over all the distribution, plus some noise variable that could be adversarial, right? So because we cannot assume that we have access to the exact gradient over the population, we introduce some noise variable, And it turns out that when the distribution over the inputs is uniform, so the input bits are chosen uniformly at random, this Nk parity problem is hard to learn with noisy gradient descent. And this does not depend on what exactly you're trying to optimize with this algorithm, right? So any architecture, any problem you're trying to optimize using gradient descent would not converge essentially on this problem, and I'll be more specific on what it means that it's hard for a noisy gradient descent, but generally this means that you need to take an exponential number of steps in order to converge, right? And more generally, this uniform parity problem is hard for any algorithm that uses statistical queries. So if you're not familiar with statistical query literature, a statistical query algorithm is an algorithm that instead of using examples uses queries from yes. Do you want to ask something?
Am I audible?
Yes.
Okay. No, my microphone wasn't working. Anyway, I just wanted to clarify some small things. So generally, learning parity is not hard, right? Like just learning parity without gradient descent, and learning parity with noise is considered hard, right?
Yeah.
And learning with gradient descent kind of falls in the same category as learning with parity with noise.
Okay, good question. The short answer, I mean, okay, so this is kind of like a harder setting. Okay, so let me repeat this. So the general problem of learning parodies when there's no noise in the label, this is a problem that I presented, could be there's an efficient algorithm for solving this this problem. This is just doing Gaussian elimination over the field of the field of 0, 1. When there is noise in the label, this is conjectured to be a hard problem, but this is assumed to be a hard problem. In this case, we're not assuming there's a noise in the label, but we're assuming that what the algorithm does is it uses only statistical queries. So all the algorithm can do is send a query, which is a function from labeled example to some bounded range, and it receives an answer, which will be the expectation of the evaluation of the query, plus some small adversary noise that is bounded by 10. Okay, so this is the framework of statistical queries. So we're limiting here the algorithm. So you cannot use any algorithm, any machine learning algorithm that you want. You can only use these type of algorithms that use statistical queries, and gradient descent just falls into these types of algorithms. And here we can prove that the number of steps that you need to take is exponential in the size of the parity, and this does not depend on any kind of hardness assumption. Okay, so this is in some sense a different result than the hardness of learning parities with noise.
Yeah. So yes, I was familiar with the SQ learning thing, but I did not know about its relation to gradient descent. I guess I've seen it in paper. Yeah.
Yeah. Okay.
Thanks.
So there's some minor details that I will not discuss here, but generally, if you're framing gradient descent correctly, then it falls into the framework of statistical query learning. Then it suffers from the lower bounds of statistical queries, and in some other settings like SGD, you can show similar results. Okay, any other questions about this?
I have one question.
Yes.
Is the entire task the task that is being learned, or is it known that it's parity of a subset and we're only learning which subset it is?
Yeah, so we're going to assume, okay, even if you know that you're looking for a subset of size k, this problem is still hard. It's still going to be you're going to suffer an exponential dependence on K.
You do
right.
know that it's parity of whichever subset.
Okay, so you do know in what context. So in the context of the lower bound, you're allowed to, we show that even if you know that this is what you're looking for, this is not going to hold.
Okay.
Even if you somehow bake this knowledge into the architecture or SGD. And our positive result, we're not going to assume anything about knowledge of this size. Okay, maybe just in the learning rate or something, but not we don't bake this knowledge into the architecture or the optimization. Okay.
Thanks.
But the lower bound works even if you know the size of the set. Okay. Any more questions about this? Okay. So yeah, uniform parities are generally hard for gradient descent, and just to kind of give hand waving argument to why this is the case. So the parity functions, I'll give some more details in the next few slides, but the parity functions are orthogonal with respect to one another, which means that the two different parities have zero correlation. And so if you take two different parities and you compute the expectation over the uniform distribution, then this is going to be just zero. So you can think of like this high dimensional space with a lot of orthogonal functions or orthogonal vectors, right? So there are n choose k parity functions, which is grows exponentially with k. So there are many uncorrelated functions, and a statistical query or a gradient descent step, let's say an initialization, is kind of just shooting randomly towards one of these many orthogonal directions, and the probability that you're going to hit the right one with the significant correlation is very, very small. So there's a lot of uncorrelated functions, and gaining even some correlation with one of these functions is very unlikely. This is kind of like the intuitively why parities are hard. I would not get into kind of the formal proof of these kind of results. And the same lower bounds could be applied to SGD, which is to say when we're not accessing the population gradient, but instead computing the gradient based on an empirical sample of examples. And here again, we're looking at noisy SGD, and there's a reason for this, again, to fit this into the statistical query framework. And we can show, again, I will not go into the details of this result. We can show that even noisy SGD, when the batch size is large enough, suffers from this same lower bound. So we need an exponential number of steps to solve the problem with SGD. Okay, so we have a similar bound for SGD, but with a large batch size. This is something that you need to assume. Okay, so these were all in a sense known results, and now we're what we want to gain from these results is some knowledge about learning parities with other models, not focusing on the learning algorithm, but focusing on the model that you're trying to learn with. And the main message of the work would be a comparison between the behavior of learning parities with SGD over neural networks versus learning parities with kernels or with linear models. What's interesting about these hardness results from gradient descent or statistical queries, that they can, in a sense, give us they give us, in some sense, immediately hardness results on learning with kernels and with linear models. And the reason for this is because what we claimed is that noisy gradient descent will fail to learn uniform parities independently of what exactly you're trying to optimize. Okay, so it will fail on any architecture. Specifically, it would fail on a linear model. Okay, so by a linear model, I mean a mapping of the input to an inner product of some features, some embedding of the input into a higher dimension feature space, inner product with some linear function, some set of weights, right? So X is mapped to inner product of psi X with W, where W is what you optimize. Okay, so this could be just linear functions or kernels or random features, as long as you're fixing your feature map in advance. Okay, so why these results imply hardness of learning with linear models? So essentially, the following, there's this following simple argument. Noisy SGD would find the optimal parameters for linear model. This is, okay, so there are some caveats here, but in general, we can prove this. And this would happen in polynomial time. So SGD is a good algorithm for optimizing linear model. However, we just claimed that noisy SGD would fail to solve the parity problem in polynomial time. And this does not depend on what you're trying to optimize. And what this means is that the optimal parameters for any linear model cannot approximate parity, right? Because SGD is a good optimizer for linear models. And if it would, if linear models were good in parities, then we would be able to solve parities with SGD uniform. Is this argument clear?
Could you clarify the first bullet point? Like, is this talking about like the kernel regime of neural networks? Is this related to that, or?
Yeah. Okay. So you can translate this to. I'll talk about the kernel regime of neural networks, but let's now just focus on kernels, right? You're optimizing W. So we have your model. What you're trying to optimize is this W here. Okay. So your model is X is mapped to psi of X times W, and you're trying to optimize W. And this is just, this is a convex problem when the loss is, okay, so I'm assuming the loss here is convex. But when the loss is convex, this is a convex problem, and this can be solved with SGD, right? This has nothing to do with neural networks. Okay. But you can translate these results to the NTK regime. I'll talk about it. Okay, but so far we just did the first bullet point, just stating something that should be common knowledge that, convex problems can be solved with SGD. Okay, and since convex problems can be solved with SGD, we can find the optimal W, but this optimal W would not be good enough because we have these lower bounds on SGD, right? So this directly tells us that linear models are not going to be good, or kernels or random features, NTK, they're all not going to be good in approximating the parity problem. Okay, I'll show this more formally in the next slide. Okay. Other questions on this? Okay. Yeah, so I'll just state this a little bit more formally and maybe go over the proof fast. So we have some input, we have some feature map of the input. So we map the inputs to a bounded range of features. And we define the class of linear functions over this embedding psi to be all the linear functions with bounded norm. So we assume that the norm of the linear classifier, this vector W, would be bounded. So we bound the number of features and we bound the norm of the linear function. And we define the loss of the hypothesis in this class of functions to be just the expected loss over example sample from the distribution or from the uniform distribution with respect to some target function. Okay. Okay. So and this is the result that we have in the paper. So for the uniform distribution, some convex loss that satisfies that the loss at the point 0 when your classifier always says 0 on all points is some fixed number L0, and the derivative at 0 is going to be minus the label -1. Okay, so the hinge loss satisfied this, and square loss and a lot of loss functions satisfy this. So for every fixed embedding, there's going to be a Nk parity function such that the minimal loss that you can get with any hypothesis in the class, so any once you fix the embedding, any choice of linear function over this embedding would give you a loss that is lower bounded by this L0, which is just the trivial loss, the loss that you're getting when you're always saying 0. Minus something that decays exponentially with k, right? So unless the norm of the classifier or the number of features depend exponentially on k, what this means is that your linear model is going to have a worst case trivial loss on the parity problem. Okay. Is that clear? Do you want me to clarify something here?
L0 should be 1/2. Is it 1/2?
Okay, so it depends on your loss. So if you're doing square loss, this would be 1/2. Hinge loss would be 1.
Yes.
Right. So we're analyzing hinge loss. So in our case, it's going to be 1, but it depends on the loss. It's a fixed number for most loss functions. But I just call this the trivial loss, which is the loss that you get when you're outputting 0. Okay. Okay, so this is just saying that kernels or random features or the Nk or all these models are going to get a trivial loss unless the number of features or the norm is exponential in the size of the parity. Okay. Yeah, so I guess I'll skip the proof. It basically boils down to, if you're familiar with statistical query results, it's kind of similar to what you get there. It boils down to bounding the correlation, the expected correlation with all the possible Nk parities, and then using this to bound, to upper bound the gradient at initialization. So essentially what we're showing is that the gradient at initialization for this linear model is going to be extremely small with high probability, right? And then this using some convexity argument just gives you the result. Okay. Okay. So again, to summarize, so we showed that any kernel or any linear model cannot approximate parities once you fix the kernel. And this is, again, true for any kernel. And this is an approximation result. So it doesn't depend on how you're optimized, right? This is, any choice of a linear function over a fixed embedding of the input would suffer from this lower bound. Okay. And you mentioned the Nk, so I'll just talk about this briefly. This was kind of like the initial motivation for studying this problem. So there was a lot of literature about the Nk or training neural networks in the kernel regime. So basically, what a lot of people claimed is that although we cannot understand the full trajectory of SGD in this kind of highly non-convex problem of optimizing neural networks, when we're staying close to the initialization, the neural network really behaves in the kernel regime. So it behaves like a linear model, depending on the gradient of the function at initialization, right? So this is just first order Taylor approximation in some sense of the behavior of the function. If you're very, very close to the initialization, then you behave like a linear model over this kernel that's called the neural tangent kernel. And in some setting, you can show that the convergence is so fast that you don't leave this regime. And in a sense, everything could be analyzed in the kernel regime. So you don't need to understand neural networks. You only need to understand kernels. And this is something that we understand quite well. So we can reduce everything to learning with kernels. And then, okay, so we showed that our result implies that no kernel, and this includes the Nk, can learn or can approximate parities. And the following interesting question is, okay, is what happens for neural networks that are trained with SGD. Okay, so when you're allowed to leave this kernel regime, anything can happen, and possibly neural networks can be able to learn parities. Okay, so this is the main question for now. Okay. Questions about this? Okay, so this was the lower bound or negative result for linear model, and now we want to show a positive result. We want to show that neural networks are able to learn parities, at least in a subset. So a warm-up exercise, maybe you're familiar with this and maybe not. Okay, in order to learn parities, you need to be able to express them first. So can neural networks express parities or approximate them? Of course, it depends on the architecture, but we're analyzing a very simple architecture of one hidden layer network or densely connected network. And the idea to approximate parities with this architecture is, okay, so we can think of parity as summing the relevant bits and then taking a modulo 2. And what you're going to do is use the first layer to sum the relevant bits, and then use the second layer to compute the modulo 2 operator. Right, this is you can formalize this pretty easily, but it turns out that two dense layers or one hidden layer of n neurons and basically any activations you choose would be sufficient to express parities pretty easily with neural networks. Okay, so this is we can check this. Okay, but we don't care about, or we don't only care about expressivity. We want to actually show that you can learn neural networks, learn parities with neural networks. Okay, so one problem in showing that neural networks can learn parities is, well, we had a lower bound just a few slides ago showing that when the input distribution is uniform, you have this exponential dependence on K for SGD. Right. So unless we're changing the input distribution, we won't be able to solve this problem. And then we need to, in a sense, we just need to take a different distribution over the inputs in order for us to have any hope of learning parities. Okay. So what we do, so the uniform distribution is hard. This is what we claimed. Instead, we're looking at the bias distribution, which is, instead of taking each bit with probability 1/2, we're going to take a slightly biased distribution. So we're going to take +1 with probability 0.6 and -1 probability 0.4. And in this case, the relevant bit, the important bits of the parity are going to be correlated with the target function, unlike the uniform case where we don't have these correlations. And this is just an experiment to convince you this is with a simple Rayleigh neural network. You're training over the uniform distribution, you're staying at random chance level, but when you're adding this bias, you're very relatively fast recovering the parity, and you get to 100% accuracy on the test set.
Could you explain what you mean that the relevant bits are correlated to the target? I mean, are only the relevant bits more likely to be +1?
No, okay. So in this distribution, all the bits are more likely to be +1, but it turns out that this makes the correlation of the relevant bits higher with the target. I will not show this, but this is a rather simple exercise. It's going to be more correlated with the target.
Do you have some intuition so that we could follow why high level, or is it a very counterintuitive mathematical?
No,
kind
it's very simple. Okay, let me see. See if I can quickly hear this. Okay. Can you see this?
Yep.
Okay. So let's see if I can. illustrate. Okay, so we have this. The parity function is just a product of the bits in the parity, right? And then if you're looking at some bit that is, I'll look at this function, the xi, which is some input bit, times the parity expectation over the input distribution. Okay. So this is just saying, okay, this is the expectation of xi times the okay, let's call this xj, ja, right? Which is okay. So there are two cases here. If I is in A, right, this is going to be just the product of everything except of I, right? Because all the bits are okay. X is in plus minus 1 to the n. Yes, sorry for my writing here. Okay, so this is just all the bits except of the ith bit, okay, because xi cancels out, and this is if I is in A, and otherwise it's going to be the product of all the bits plus the ith coordinate. Is this clear, or are you with me, or?
I'm with you.
Okay. So we're just taking, if the bit is part of the parity, then you're taking a product of all the bits except of this ith bit, and if it's not part of the parity, then this adds up to the bits. Okay. And if this would be true. Okay, if we're taking an unbiased distribution, this would be just 0, right? And if we're taking a biased distribution, this would be something, I don't know, alpha, right? So an expectation of over this, okay, because all the bits are independent, this turns out to be alpha to the k minus 1 if I is in the relevant bits, and alpha to the k plus 1 if it's not. Okay. Right, and this is just plugging in this expectation. Okay, so you're going to have more correlation with for the bits that are part of the relevant subset. I don't know if this is a good intuition or just if you're tweaking the distribution, the problem is that the uniform distribution, you have no correlation with anything. Once you're changing the uniform distribution, then correlations are starting to appear, and the bits that are actually contributing to the target function have more correlations than the ones that don't. Okay.
So basically the conclusion is that if you're is the intuition that if you're comparing two bits, like you want the bits that are actually important to be more correlated because gradient descent is going to care about them more. And here you have like a factor of alpha squared more correlation on the relevant bits.
Yes. So yeah, gradient descent picks up these correlations very early on. So if you have more correlations with the right bits, these are going to kind of rise above the rest. We're actually okay. So in fact, we're analyzing an even simpler case than this distribution. We're analyzing and I would say a more extreme biasing of the bits. And in this distribution, the distribution that we're actually analyzing in this first paper that I mentioned, we're sampling all the bits uniformly with probability 1/2. So half of the distribution is just the uniform distribution. And the other half, we give all the relevant bits either are all +1 or -1, so they are highly correlated with one another and to the target, and the irrelevant bits are just uniformly sampled. So this is kind of an even easier case, and here you can the correlation is just constant for the relevant bits, and it's 0 for the irrelevant bits, and then gradient descent is going to pick on this correlation. Okay. Okay, and okay, so this defines the distribution, this kind of half and half, half uniform and half this kind of tweaked bias distribution. And we're training a one hidden layer ReLU 6 network. So this is a clipped version of the ReLU. We need the output of the activation to be bounded for the analysis. This is just a one hidden layer network, a very simple network, and we optimize using gradient descent on this problem. And what we show is that for large enough value of n, and for an k that is smaller than the 10th root of n, so k needs to be significantly smaller than n, but still it could grow together with n. For any choice of Nk parity, when we're training a one hidden layer ReLU network of polynomial size for a polynomial number of steps, so we have polynomial dependence on all the parameters of the problem, then this optimization finds a function with a small enough. Okay, so unlike the case of kernels, here we have convergence in polynomial time in the parameters of the problem. And the idea here is, again, that the input bits are going to be, the relevant bits are going to be correlated with the target, and the irrelevant bits are not going to be correlated. So we have this kind of difference between the behavior of the relevant and irrelevant bits. And essentially, the first gradient step that we take would separate the relevant and irrelevant bits, and then the rest of the optimization would just learn a linear function over this good representation. And okay, so this was the positive result for neural networks. We said that we can learn this problem that we just defined in polynomial time. And what happens for linear models or NTK or kernels? Since half of the distribution is the uniform distribution, and we claim that this would be hard to approximate for any linear model, this means that on the uniform part of the distribution, no kernel method would achieve an error that is smaller than trivial. And this gives us the following result, which is, I guess, the main result of that this all was leading to, that there exists a problem such that gradient descent on neural networks achieves an arbitrarily small loss in polynomial time, but no polynomial size kernel can achieve an error below some constant. Okay, so there's this large gap between what you can do with neural networks and what you can do with kernel machines. Okay, so it's in a sense important to leave the kernel regime if you want to kind of enjoy the full potential of what you can learn with neural networks. Yes. Any questions on this? Okay. Okay, so this kind of sums up the first paper. The second paper, okay, so we gave this result, the separation result between kernels and gradient descent with a somewhat contrived distribution. So we had to kind of play with the distribution enough so it would be easy enough for gradient descent, but hard for all other models, for the linear models. And the problem here is that we kind of, in some sense, baked the answer into the input distribution. And what we would like to do is to achieve a similar result with a simpler distribution, maybe just a biased Bernoulli distribution. Okay, so just each bit has a small bias to be positive, like the one I showed with the experiments. And we can do this. Okay, this is another paper. We'll just mention this. We can do this. We can have a similar analysis. We can show that neural networks can learn this, but the architecture is somewhat contrived. You have to kind of like bake the parity problem into the architecture. But I think this is, I mean, you can probably achieve similar results in this setting for a simpler distribution. Okay, and the nice thing here is this can give you sort of like a maximal separation between kernels and neural networks. So this is a distribution where neural networks would get to effectively 0 error, but kernels would get the higher error that you can assume, something that is very close to the trivial error. Okay. All right, so any questions about these works so far? Okay, so now you have to tell me how long do you want to go. I mean, what's your time frame? Or you can stop me when you get tired.
I personally will probably have to go in 10 or 15 minutes, but I can make someone else host to keep the room going, depending on what people have.
Okay, so let's aim for this 10. I'll go briefly on these results, and then whoever wants to stay for a discussion, I'll be happy to stay around. Okay, cool. So this was all previous works on a comparison between neural networks and tangent kernels, and now we're going to go back to the uniform distribution. Okay, this is the hard distribution for learning parities. We have lower bounds on the uniform distribution, and we said that for gradient descent or SGD, we need an exponential number of steps to solve the uniform parity problem, where the exponential dependence is on the size of the parity. Okay, so we had this subset of size k, and we need an exponential dependence on k. Now, if k is very small, I don't know, 3, 4, 5, 6, this, we're optimizing, large network, spending a lot of GPU time. This is not too terrible for taking k to be relatively small. And one question we can ask, okay, this is a lower bound. This means that you need to take at least n to the k steps. But what is the upper bound? How many steps effectively do we need to take on this problem in order to solve the parities in the uniform case, when the hardest case for solving parities? And we can ask whether SGD can learn to solve uniform parities for small sizes of k. Okay, so let's do this experiment. We're fixing n, the number of bits, to be 40, the size of the parity to be 20, and we're running a one hidden layer railing network on this problem, and it doesn't converge. It stays with random guess performance. And we're doing the same with n equals 40 and k being 4, a much smaller size of parity. And it seems like we get the same behavior. You can't tell the difference between these two graphs. They both seem to be behaving the same, staying at random chance performance. But if we just keep on training, and this is something that is very interesting, it was observed in other contexts as well. If you just keep on training, okay, well, when k is large, then you never converge, and this is, we're not surprised because we have these hardness results for lower bounds. But when k is small, we see this jump in performance, and essentially it solves the problem very quickly. We have kind of this phase transition where it seems like nothing is happening until a certain point of time where we just solve the problem. And we see this across different architectures, on ReLU networks, on transformers as well, on other architectures that we're trying to, that we try this problem on. When we tune the size of the parity correctly, indeed, it takes you a while to get to a point that you're even doing something, but once you're starting to progress, you kind of immediately solve the problem. So there's like this phase transition and solving the problem, like the network suddenly gets it at one point of time in the training. Okay, kind of like this aha moment in learning of Parities. So the main question that we're trying to understand, figure out here is, okay, what's going on? So we have this kind of phase transition behavior in learning Parities. Everything, it looks like, you know, you're only doing random guesses until a certain point of time where you just solve this problem. If you've seen this grokking paper, this somewhat similar to what's going on there. And we're trying to understand, like, maybe one basic question or one basic hypothesis here is what's going on. Either there's some kind of random search, so there's no progress at all throughout the training, so you're just kind of walking randomly in space until you hit a point in the lost landscape where you just kind of fall into this hole in the lost landscape and just solve it. So there's essentially, you're just randomly roaming around until you find a point with a small loss and then converge. This is one possibility. The other option is there's some kind of hidden progress. So we don't see this on the surface. We don't see that it looks like the network doesn't learn anything, but under the hood, there's something going on that makes you converge into the right direction. So the mental image here would be that you have a slope that is very, very small, and you're kind of doing this biased random walk towards the right solution, but very, very slowly in a way that it's not significant in the loss landscape and the behavior of the loss. Okay. So starting to work in this, I personally was in the belief that everything that's going on here is just random search, but we had kind of more and more accumulating evidence that, in fact, there is some hidden progress in this problem. And although it doesn't seem like it at first, the network is always kind of progresses in the right direction and not just randomly roaming around. Okay, so yeah, let me just skip this math. You're probably too tired for this anyway. So essentially, so I would not go through the analysis, but essentially we're analyzing the same, very similar architecture to what we analyzed before, one hidden layer dense network. And what we're able to show is that at initialization, if you look at the population gradient, the gradient over all the distribution, there is a small bias, or the correlation or the gradient with respect to the relevant bits is slightly larger than the gradient with respect to the irrelevant bits. So this is very, very small, right? The difference is exponentially small in this case, but with enough steps or with a large enough batch size, you'd be able to detect this difference in correlation between the relevant and the irrelevant bits, right? So at initialization, the gradient points you very, very weakly into the right direction. So essentially what we're able to show is that SGD kind of boosts this initial correlation. So there's an initial signal right at the start, and what you're doing is you're doing kind of SGD steps to accumulate these gradients and eventually find the relevant bits by kind of boosting on these correlations. And we're able to show that you're learning these parity functions in a number of computational steps. So we're tying here the number of the batch size times the runtime. The number of examples that you need to see depends exponentially on K. So this is kind of matching, the dependence on K is matching to the lower bound.
So just to clarify, your claim is that the kind of correlation is monotonically increasing as training progresses, but this isn't reflected at all in the loss. So even with higher correlation, your loss is still at chance.
Yeah.
Okay.
Yes, so I'll show some figures on this, but essentially, yes, you have some correlation at the beginning, very, very weak, something like n to the minus k. and you're boosting on this. And when you see enough examples, when you see enough gradients, then the signal rises above the noise, and then you're converging. But you don't see this in the error. Okay. Yeah. So again, the key theoretical result here is that the initial population gradient points you into the right direction, and then you're able to use this fact to just solve the problem with this. And going back to some experiments, so we're run this across different architectures, and we're plotting here the dependence of convergence time on n and k, and we see again this exponential dependence on this size of the parity k that matches the lower bound and upper bound that we have. Okay. So yes. So okay. So what I claimed is that, as you mentioned, there is some hidden progress that you cannot observe in the loss or in the accuracy, but something under the hood is happening, and we want to try and measure it in some sense. Here we're plotting. So there the gray lines are the irrelevant bits, the values of the weights of the irrelevant bits, and the pink ones are the relevant bits. And you can see that they move kind of very slowly, but they start diverging. The relevant bits start becoming larger and larger than the irrelevant bits until a certain point of the training where they just converge to their maximal values. And throughout, you don't see this in the drop of the loss or the error, right? So just looking at the error, it seems like nothing is happening. But if you know in advance what are the right weights and you're kind of tracking them, you can see that they're moving, maybe even right from the start, moving in the right direction until they reach a certain threshold where just everything is solved, right? So we can kind of like look under the hood here and see that this progress is in fact happening. And on the right here, we're giving some measure of progress, which is the distance of the farthest weight from the initialization. And you can see that this progress measure indeed increases throughout the training, while all the losses, or the loss and the accuracy stays the same. Okay, I'll skip this. Yeah, okay, and some other experiments to try to convince that what's going on here is indeed hidden progress, and not this random search. So on the right, we have these different plots of the trajectories of different runs when we're fixing the initialization. So all the different colors are different initializations, and the same color would be the same initialization, but different choices of the examples during the training. And you can see that the initialization pretty much determines when you're going to converge. Although it seems like nothing is happening throughout, the point of initialization really determines how good you're going to perform, how fast you're going to converge. Okay, so this is on the right here. On the left, we have these plots for different values of n of the distribution of the iterations it takes you to converge. And what's interesting to note here is, okay, so there's this long tail of unlucky initializations, but there are no initializations that are extremely lucky. So it's a very essentially you don't see any initialization that just lands very close to the right solution. So it takes you a while to boost on the signal, and just reinitializing does not help you solve the problem faster. Okay. Questions on these plots or the previous ones? Okay. Okay, so this all these results were for what I call online Sda. So each iteration, you're getting a fresh set of examples. we also have experiments for offline Sda, so where you're fixing the sample size and then just iterating over this this fixed sample. And here, if you're, I guess you've seen this grokking paper, here you're seeing a very similar phenomena where the train error drops essentially very fast to 0, and then the test error stays at random guess performance and then drops at a certain late point of time. Okay. So I guess I'll finish here. If you have any questions, then I guess we can stay for another discussion, or I can just conclude.
Great. Maybe we can thank the speaker and then I'll stop the recording and we can do questions offline. So yeah, thank you.
Thank you.